Swayam Prabha. Digital India. Educated India.
Welcome to week 2 of our computational neuroscience course. So, over the past few lectures, we have gone through the introduction, that is sort of more of the biological uh, introduction about the course. That is, we have discussed the structure of neurons, what is an action potential, the structures present in the brain, the broad structures there, how we record activity from neurons, and what we mean by activity is basically the membrane potential of neurons. So, in this week's lecture, we will be talking about the excitable membranes and neural activity in more detail with mathematical treatment of membrane potential and what spikes are and so on. And we will go into the details of how action potentials are created, how current injection is happening in a neuron and so on, to in order to understand the dynamics behind the creation of action potentials. And also we will understand how synapses act and how action potentials are communicated across from one neuron to another, and all this will be done with a quantitative understanding. So, what we have been discussing so far is that we have introduced the idea of the action potential, and we said that it is the membrane potential of the neuron, that is the membrane potential. If we have a neuron, then the V in, or the potential inside the neuron, minus V out, that is the potential outside the neuron, that is what we will call as V, and or the V membrane or delta V, as you may recollect. And this delta V is what contains anything to do with computation by these neurons. And we had said that Hodgkin-Huxley showed how this delta V can produce has signatures of the currency of computation, which is spikes or action potentials, nearly in the middle of the last century. And these events or action potentials are also called spikes, and these are the ones that are also communicated across synapses when based on the release of neurotransmitters and uptake of neurotransmitters on the postsynaptic neuron by the postsynaptic neurotransmitter receptors. So, we have a particular thing here that says record, and we have understood how we record the different activities, the different ways in which we can record activity from neurons, and it is ultimately this membrane potential that we are recording that becomes the most important. So, let us delve into how this membrane potential is actually created in the neuron, and how this changes with time. So, if you recollect from your high school chemistry, if we have a semi-permeable membrane, let us say with an aqueous medium, and this semi-permeable membrane is separating the aqueous medium on the two sides. Let us say we have particular type of ion I on one side, and the same ion um, on the other side, but on the right hand side, let us say it has a concentration of C2, and on the left hand side it has a concentration of C1. Now, since this is a semi permeable membrane, that is the ion can flow across the membrane, and depending on the amount or the concentration of the ion on the two sides, there will be a flow of ion from the higher concentration to the lower concentration side. However, as there will be a difference in the amount of ions on the two sides, there will also be a potential that will be developing on the two sides. So, if we say that if as the ion moves from one side to another side, it is the chemical potential that when it is counterbalanced by the electrical potential, at that time this ion I becomes comes at equilibrium. And let us say that this equilibrium is reached when the potential on the left hand side is V1 and the potential on the right hand side is V2. So, if we let the ions sit in this aqueous medium, and let us say if the concentration C1 and C2 is maintained, that is, it is large enough, ultimately when the potential difference V1 or V2 minus V1 is equal to a particular V equilibrium, or we will call V reversal potential, V rev or VEQ for that particular ion, that this ion there will be no net current flow across the membrane. So, if we think of it in this way, that the total electrochemical potential on the left hand side, if we write it as mu 0 ion I, or rather mu I 0 plus C R T log C log C I plus ZF VI. So, for the ion I on the on one particular side, if we say the side is 1 here, then this particular we set it by the superfix 1. This is the electrochemical potential on the side 1, that is on the left hand side, and this has further terms if we allow the free energy to, if we allow the potential to have include the pressure and temperature and other forms of way in which this free energy can change from on the left hand side. Similarly, on the right hand side, we have mu I, the ion 0. On the side 2, it is also going to be the same, because this is the molar free energy, and that is essentially in this case the potential of the ion at unit concentration and 0 potential. That is, if we have the concentration of the ion I to be unity in this framework with the proper units, and similarly if the potential is 0, then the overall potential in the ion is this mu naught, and that is not going to be unchanged on the two sides, and it will be additionally the electrochemical potential on the right hand side will have the term Ci2 plus Zf Vi2 plus the other terms, which we will assume to be constant on the two sides, that is terms due to pressure, temperature and so on, and they will not come into the picture. So, when the two sides, the ions are at equilibrium, this electrochemical potential must balance each other out. So, in that sense, if we write that down, that means this, if we equate the left hand side electrochemical potential to the right hand side electrochemical potential, and this mu 0 is going to cancel out, and so we are essentially left with RT log C1. Let us drop the suffix I and return to this particular form of writing the concentration, that is C1. We are assuming that it is only ion I here, and plus ZF V1. Again, we are dropping the suffix I and replacing the V1 I by V1, and this will be equal to RT log C2 plus ZF V2. So now if we relate if we take the move the ZFV to the other side, we will have V2 minus V1 is equal to RT by ZF log of C1 by C2. And this, if we have a particular concentration of an ion as C1 on one side and C2 on the other side, then this equation on the right hand side of the equation provides us the difference in the potential on the two sides, that is the V2 minus V1, that is the difference in potential in between in the two sides, at which the ion will be at equilibrium, and so there will be no net current flow across the membrane. So this essentially is what we will call for an ion as the equilibrium potential V EQ or V E, or also the V rev or the reversal potential of the ion. This this is basically a sort of a marker to tell us how ions will flow across a membrane if there is a path available for ions to flow. Then what amount of current will flow across the membrane, or in which direction that ion will flow, will be determined by the actual membrane actual potential difference and the reversal potential for that particular ion. So for neurons, as we had mentioned earlier, the key players in terms of the ions are sodium, potassium, chloride and calcium, of which we will see that with the sodium and potassium ions only a lot can be explained. So how is the membrane potential, what is the membrane potential for neurons? So it will depend on this C1 and C2, or C concentration outside and inside of each of the ions, and finally if we have the ions, all the ions at rest, that will determine what the potential, membrane potential of the neuron is going to be. So the concentrations present in the neuron, inside the neuron, for sodium, potassium, chloride and calcium are approximately the values given here, that is 20 millimolar for sodium inside and 120 millimolar for sodium outside. Similarly, potassium, the amount of the concentration of potassium is extremely high in the in the inside of the neuron, and it is low outside the neuron. So sodium and potassium have the exact opposite nature of their chemical gradient. That is, if the concentration were the driving factor, then potassium would be flowing out of the neuron because of the high concentration inside, and sodium will be flowing into the neuron because of the high concentration of sodium outside. And similarly, chloride has the similar nature as sodium, that is the chloride concentration is low inside the neuron and very high outside the neuron, and calcium too is extremely small in terms of its concentration inside the neuron and outside the neuron. So, if we now use our idea of V2 minus V1 is our V equilibrium or V reversal, then this will be determined by RT by ZF um, log C1 or C out by C in, and this is my V in minus V out. That is our the way we will be defining membrane potential. So, when the membrane potential will be this VE for that particular ion, let us say sodium, then the sodium will not flow across the membrane, that is, it will be at equilibrium. So, given that Z is unity for sodium, potassium, we will replace the Z by +1. For calcium, it is +2, that is the amount of charge there, and for chloride, obviously it is -1. So, accordingly, this Z will be plugged in. R and basically RT by F at 25 degree centigrades is known, and that is around 59 millivolts if we take this as log 10. And so, that allows us to calculate what the V equilibrium is for sodium, potassium, chloride and calcium. So, what we see is, if we calculate, then the approximate values of the equilibrium potential of these key ions are +45, -90, -75 and +120. So, what does this actually mean, that it is +45, -90, -75 and +120? As we have been saying, if the membrane potential, that is this V in minus V out, is equal to +45 millivolts, then sodium cannot flow across the membrane, or rather the net flow of sodium will be 0 across the membrane. That is, the amount of sodium going out and coming in will remain equal. Similarly, for potassium, if the membrane potential is -90, then it will then potassium will not flow. Similarly, for chloride and calcium. Another way to think about these numbers is that if we have the potential of the membrane at a particular value V or V membrane or delta V, then it is the equilibrium potential of that ion that will determine which way the ion will flow. In other words, if a path is available for the particular ion in question, let us say we are considering sodium ions, and let us say sodium at a particular voltage V, if there is a possibility of sodium to flow across the membrane, then the sodium ions will flow in a direction such that the voltage V is pulled towards this +45 millivolts. So, let us take a step back. We have said that earlier there is a resting membrane potential, and so that means that at equilibrium, that is when the neuron is left undisturbed, the membrane potential stays around -60 millivolt. This can vary from neuron to neuron and based on state, but it is approximately around this value. So, between -50 to -70, sometimes even lower. So, we are saying that this is at rest. So, if there are paths available in the membrane for sodium to flow, at rest, sodium will flow across the membrane in such a way that this -60 millivolt is pulled towards plus 45 millivolts. That is sodium's reversal potential. But we are saying that it is at rest. So, therein comes a contradiction. So, that is, there is no sodium flowing at that time, or it is, at least it is at rest in the sense that the net ion flow across the membrane is 0. So, that means that the sum total of all the currents, that is, if we have the total current as I sodium, that is the amount of sodium flowing, I potassium, that is the amount of potassium flowing across, or the net amount of potassium current across the membrane, and I chloride and I calcium and all the other ions, this net current across the membrane would be 0 at minus 60 millivolts. So, even though the at rest, the which is the membrane potential is minus 60, and it is not equal to the equilibrium potential of any of these ions here, we are still at rest, because first thing is that it is actually the net current flow is 0. Further, it is also determined, we had implicitly been saying this, that if there is a path available for that particular ion across the membrane. So, that we will later on see is determined by the ion channels and the probability of those ion channels being open at a particular voltage, and we will discuss that in great detail later. And so, the current, the sodium current flowing at minus 60 millivolt is not simply determined just by this plus 45 millivolt and its difference from minus 60, but also the conductance present in the membrane, which will allow the sodium to flow or not flow even. So, if at minus 60 millivolts, the path for all the sodium, for all the paths for sodium to flow inside or outside of the neuron is 0, and that is, there is no path available, then this INA also would be 0. In fact, what we will see is that there is a very small conductance for sodium at this resting membrane potential. Similarly, for potassium also, it is actually a very small conductance available at minus 60 millivolt for potassium, and hence at rest the minus 60 millivolt membrane potential is not pulled towards minus 90 millivolt by the potassium ions. Similarly, the chloride ions and the calcium ions all have very low membrane potentials, I am sorry, very low membrane conductances at this potential, and it turns out that the voltage adjusts itself such that this net current flow turns out to be 0, and that is what we mean by the resting membrane potential. So, the concepts that we have here is that we have a particular reversal potential or equilibrium potential for each ion, and this equilibrium potential or reversal potential guides us to think of the way the ion, that particular ion will flow when the membrane potential is different from that equilibrium potential. So, when the membrane potential is different from that equilibrium potential, the ion will flow in such a way that the membrane potential will go from the particular value to the equilibrium potential. So, and at rest it is minus 60 millivolts, and so that happens because the net current is 0 at that point, and that current is determined by the amount of conductance available of the for the different ions at play at that particular potential. So, it is we will go into more detail about this process in later lectures when we go on, but here the main point is to understand how the membrane potential is created and how it changes depending on the membrane potential itself, or the how the conductances change and so on. So, just to tell us, we have been saying that the membrane potential is pulled towards equilibrium or equilibrium potential. So, let us say the membrane potential is minus 40 millivolts, and at that time there is sufficient sodium conductance available, let us say. So, that means the direction in which the sodium ions will flow is that such that the minus 40 millivolt is made to go towards plus 45 millivolts, and that means the sodium being positively charged, it means that sodium will go into the neuron from outside to inside, that is positive charge will go in, and that will create the potential, or that will cause the potential to go higher towards the equilibrium potential of sodium. Similarly, if let us say the membrane potential is minus 40 millivolt, and let us say a substantial amount of conductance for potassium is present, and so the potassium equilibrium potential being minus 90 millivolt, the potassium will flow in such a direction such that this minus 40 millivolt is pulled towards minus 90 millivolt. So, again, as potassium is positively charged, it will flow from inside to outside of the neuron in such a scenario. So, that the membrane potential or the potential inside is gradually lowered compared to the outside, that is the positive charge is going out of the neuron. And chloride similarly will actually try to flow in the same scenario because of its negative charge. It will do the same thing as sodium. So, with this in the background, we will next in our lectures try to understand how these ion channels or the conductances that we were talking about work in the membrane and provide paths to the different ions, and how all these together finally create action potentials depending on the current injection into the neurons through synapses or artificially when we are experimenting, as we saw in patch clamp recordings and so on. So, we will start off with the rest of the ideas of membrane potential and excitable membranes in the next lecture. Thank you.